Recording in progress. All right. Okay. So I was giving 2 talks, as you know. So these are really in the spirit of a sort of review of a body of work that goes back to around 2014, and then sort of culminated last year in an experiment done with the Google AI group. It's my own experience that since it's not an area that people have necessarily followed in detail, so hopefully in giving a somewhat tutorial talk, I will not be insulting any of you, except maybe I use it, and you as well. But anyway, that's what these are my friends, I can insult them. But I'm sure there are lots of other talks which are hot off the presses. So I want to talk about in this talk sort of the idea of Floquet phases, and then build up to an Ising model of the phenomenon, which this thing at the top, right, should go away.
There is,
Yeah,
there is a way.
that's
Can
right.
anyone remember the sequence of buttons you need to hide it?
If you go into more, there should be something to remove it.
Yes, I think I saw it actually.
Yeah.
What's
Just
that?
those 3 dots.
Three dots.
Sorry,
more.
may I just interrupt you briefly?
Yes.
Somebody in the lecture theater must have a microphone on other than the speaker, because we can hear Shivaji multiple times in a kind of infinite echo here online.
Sorry, what somebody has this is somebody unmuted in the audience?
So that's been a remote.
Okay, so that apparently it's a remote challenge
It's fine.
which has been fixed, or maybe Gunnar is the echo gone? Gosh, that's why that's floating up. Hopefully it'll disappear unless you want to listen to it. Okay, start over. So,
Well, I mean,
sorry.
yeah, I mean, I'm just logged in online, so it'd be very unusual for me to experience this on my own, right? Because I mean, my microphone is off, I think.
So there is still an echo? Are you mute video? What should we do?
Just need to turn up your volume.
Yeah, I currently hear what I
Mine?
said 30 seconds ago.
That's producing the echo.
It should be fine with its own.
Yeah, that's it.
Is okay, so I can't hear anything, but I've turned up the volume. Did that improve things?
Well, let's just continue.
Okay. All right. I hope that's better, but I'm not listening anymore. So if somebody will put something in the chat, we might learn. All right. Back to work. So I want to discuss Floquet phases, but let me just start by reminding you how standard phases work. Right. So I'm going to think about a set of qubits or spinor halves for concreteness. So that's my Hilbert space, is a tensor product of some number of them, and as usual, as anybody physicists or statistical mechanics, you will be interested in the limit in which this number gets to be very big. So H is some local permission operator. And by local, we might mean in extremis, just that the interactions or the terms in the Hamiltonian are really of compact support, don't actually on the certain number of qubits, but more general, that they have an envelope which decays sufficiently rapidly, exponentially. So what we're interested in physics-wise is that we start with some sensible initial state. Right? This is the question, because Hilbert space is an extremely large space and so therefore, if you were willing to start allowing for absolutely arbitrary initial states, right, Who knows? It should be like that.
Yes.
What happened there? I didn't do anything.
Oh. Hi, Shivaji.
Hey, Premi. Okay. All right, let's see what happens. Okay. So with some sensible initial state, which is not too strange, it could be a product state. It could be that I equilibrate the system at one temperature, and then I'm going to move to another temperature and use that as the initial state in some sort of range. We're going to start with the initial state, act on it with the time evolution operator specified by the Hamiltonian, and look at very, very long times, right? So this late time state is what we observe in experiments. And now what? So, and we're interested in its properties. Now, at zero temperature, light is very constrained in the sense that the initial state, more or less has to be the ground state. You can discuss among friends whether you ought to allow vanishing energy density, and maybe there's a little bit of give, but basically you're forced to be in the ground state. In which case it's an eigenstate, and there's no need to go to late time, so just look at the ground state. But at a non-zero temperature, what you have in mind is some state with some energy density, and I haven't written it here, but also not just an average value of the energy density, but also there shouldn't be, large fluctuation in it. So you do not, for instance, superpose as initial states which are wildly different in energy, having really different values of the energy density. And so then non-zero temperature is the statement that this energy density is, order n above the ground state energy. So it's at a finite energy density above it. And then again, we go to late times. So if the system thermalizes, right, then we know that we can study its thermodynamics, its correlations, and its response using the equilibrium density matrix, or via single many-body eigenstates of the Hamiltonian H, which is the statement of ETH, the eigenstate thermalization hypothesis. So that the system thermalizes is the statement that if I look at late times in this state that I constructed on the previous transparency, which is not really a state, because in some sense it keeps evolving, right? I mean, it's still got e to the minus IPH acting, right? But nevertheless, if I look at late times and I calculate anything of interest, that calculation will agree with calculating with either this density matrix, the Gibbs state, or just using a single many-body eigenstate and calculating that. Okay. Now, this late time equilibrium state can show singular changes. Maybe I change some parameters, maybe I change the energy density, and some aspect of the late time state changes in a singular way. And that, of course, is what we call a phase transition. So it could be a singularity in the thermodynamics, correlations, response, typically also. Now, if the system doesn't thermalize, then one option is that it's many-body localized. And for the purposes of today, and I won't even really use this, we'll think of it as there exists a family of local conserved quantities which are extensive in number. Right? And if that's true, then the system is many-body localized. In writing something like this, I've actually assumed that the only thing that's conserved in that case is the Hamiltonian itself. So we've gone from having one to n.
If some use it can be thermalized and others don't.
Right. So, but I don't want to go down the path of other intermediate options, but it's an interesting question. So, I mean, obviously, in standard thermodynamics, you could add a number, you could add various charges. So you can certainly by hand have conserved quantities, which would then have to be. The sort of question that you're sort of digging at is, are there examples where so these are emergent conserved quantities. Those are not things I build in. Those are things I get out once I've solved the Hamiltonian. It's not ones I knew in advance. So you could ask, are there cases with square root event, right? And I don't know of one. Anybody else does, they should tell me, but of course, it's an interesting question as to whether you could. A similar question is, with ETH, there's a diagonal ETH and an off-diagonal ETH. And I remember some discussion of people trying to find cases where diagonal tiles with off-diagonal. I also don't know the status of what it's doing. Yes, but these are all active questions to my mind.
Recording in progress.
Okay, so those were standard phases, which we know and love, which we get at via Hamiltonians, right? Now, Floquet phases at the 30,000 foot view are defined not by local Hamiltonians, but by local unitaries. So once you have a local unitary, which I'll explain in a minute, we're just going to repeat it, right? So the unitary will do something over some time period, and then we'll just repeat it n times, and then examine the limit as that goes to infinity. So the same idea, some initial state, go to long time, in this case, a long for periods, and then we're going to look at these late time states and try and understand what's going on. Now, what does a local unitary mean? So if you like quantum circuits, you can say it's a finite depth quantum circuit, which would mean you've got a set of qubits, you act with 2, 3, whatever, some finite number of things with some unitary, you've got some layer in which every spin is hit once, but no more than once, then you have another layer, a third layer, a finite number of these is a finite depth quantum circuit. Or if you like Hamiltonians, then you say to yourself, I've got some local Hamiltonian, which is, however, now time dependent in general. I evolve it to the state. I find the time evolution operator for a period time t, which formally is a time ordered exponential. I didn't write t down here because it would look really confusing. But it's the solution to this Schrodinger equation with the initial condition for at time 0. So that's a local unitary, and we're interested in repeating the local unitary a large number of times.
I'm sorry,
Yeah.
just a clarification. So finite depth view kind of mean that we are not scaling with the system side?
That's right.
Okay.
That's right. Exactly. Yeah. All right. Now, you might ask, that's great. You define the mathematical problem. Are there different late time states? Are there phases? Right. So of course, if the Hamiltonian is independent of t in what I wrote, in other words, standard phases are obviously a trivial subset of Floquet phases, in which any period will work because the Hamiltonian really doesn't care about the time. Right? So certainly those must exist, but of course we're interested in what if we're not just doing, what we already knew, but now we have some time dependent Hamiltonian, then we now get new phases which are generally dynamical and did not exist in the earlier problem. So naively, actually, your expectation should be no. Yeah, and why is that? Well, say, okay, I've got a unitary, at some time dependent Hamiltonian. Let me go back to my StatMech toolbox, and StatMech tells me that if there are no conservation laws in the problem, and all I had was the Hamiltonian, the energy, then the maximum entropy states, irrespective of any other constraint, has to win. The rest just the identity. It's the infinite temperature state. So it doesn't matter what time dependent Hamiltonian I write down. I expect that the late time state will be featureless, will just be the other, right? And if every time dependent Hamiltonian, every periodic time dependent Hamiltonian gives me the same answer, obviously from one phase, which is the infinite temperature problem, right? So if StatMech holds, we are done. There's nothing else to discover. A different way of thinking about it is, you can think of your time-dependent Hamiltonian as some average one plus some variation, right? Now, you're used to doing linear response theory. And in linear response theory, having a time-dependent perturbation generates some, think of conductivity, right? You have some conductivity, which is frequency dependent, right? Now, you can argue about whether in the zero frequency limit, you are going to find energy absorption or not, right? That's the question of insulators. But no one thinks that at a non-zero frequency, you're not going to absorb energy. When you expect to find sigma of omega times e squared, and sigma of omega at a non-zero frequency, then you expect it to be non-zero. So you should see Joule heating So that's a dynamical way of thinking about the same answer, that you just heat and heat and heat, and it's a bounded local Hilbert space, right? As a lattice model of its kind. You get to infinite temperature. At this point, you absorb as much as you emit, and that's it. Or more formally, if you calculate the conductivity at infinite temperature, it will come with a factor of 1 over T. And as T goes to infinity, that will disappear. So far, so good. So unless we invoke something which goes beyond statistical mechanics and standard response theory, there should be nothing to find. So, good. So that's in a locally bounded space. In a locally unbounded one, heat and heat and heat, and there you have the option of never reaching a steady state.
This is really an order of limits issue. You rather artificially did it for problem.
I mean,
You have to have a very isolated point system for this to really hold true.
right, which is why the experiment will be done on Google's quantum computing platform, which is another analytic system which is designed to do exactly that. Okay, yeah. But in any case, I'll get to with localization, that's actually less of an objection because, so this would be true here. Right. Okay, so, unitaries that do what I just described absolutely exist. And there are interesting questions about those, namely how quickly, do they heat? That can depend upon the sort of frequencies that you built into the time variation. So there's the whole topic of pre-thermalization. I couldn't see it last night. I think there's an upcoming paper by Bill Definitely, David Hughes, and at least one other person, in which they're talking very carefully about this issue for, improving finite side effects. And all of this is really fascinating, but I'm not going to talk about that too, because at very long times, you end up thermalized. Now, for such Floquet systems, actually, there's also a version of ETH, and that version is that the unitary which you repeat has eigenstates, and each and every one of those eigenstates gives you the same answer, and that answer agrees with just working at infinite temperature. Good. So in other words, systems which heat up to infinite temperature and suffer heat death are quantum chaotic or ergodic systems in the Floquet center. And they obey statistical mechanics, they have the Floquet theorem, they have ETH, everything you could want, except there's only one phase.
Outside the world of Google's machine, can you give any examples in nature where this actually occurs?
Localization?
Well, the isolated system that naturally is to.
I mean, my talk is not about this case, it's about the localized case. So, this is by way of saying I'm going to study certain models, and in those models, this is what I should expect to happen. Obviously, if the local Hilbert space is unbounded, but look, whenever you have some separation of scales, which is after all how we're building these quantum devices, I mean, you have lattice magnets with nuclear spins, all of which will eventually couple to other degrees of freedom. But of course, you can imagine that you heat up to get essentially a plateau for a long time before it heats up again. So I don't see why in any of those cases it would have to be study spin models. But there shouldn't be just a regime, which is a question of time scale.
Is there a one to you have stat max in this situation? Is there a one solution to solution for it?
So there should be, but I think because it's infinite temperature, for the same reason, I think it's just trivial.
So it's not,
Yeah.
that's when you got that response.
Right, but that was, I was giving a description of the transients. If I began with a low energy state in units of the average Hamiltonian, it was arguing that if you think in the language of response theory, then you say you repeat and repeat and repeat and repeat and stuff. But yeah, you're now asking a question about the ultimate steady state. Yeah. Right.
Thank you.
So it was more intuitive because, of course, it's a non-equilibrium process. So along the way, yeah, but it's the same intuition as complementary to the StatMap one. Yeah. Okay. All right. So it'll be ETH, and these eigenstates will all agree, and also the level statistics will be, corresponding circular ensemble of the Wigner Dyson family, orthogonal or unitary. All right. Okay. So obviously we need to find something we need to not thermalize, and so we get back to this idea that there are systems which are many-body localized. So the first question to ask is, if you're not in equilibrium, since you're so used to thinking of phases and phase transitions as involving equilibrium behavior, can you get phases and phase transitions out of it in this sense of many-body localization in the context? And so the answer is yes. And actually, this goes back a while, but I think this is another of these topics where I think the diffusion of knowledge outside the small community who works on it has been less than it probably should be. So what I'm going to do is go over some of the stuff that was in this paper. David Hughes, Rahul Kishore, Arijit, and myself from 2013, which is this phenomenon of Eigenstate order. So I'll describe it in the context of Hamiltonians, partly because it's actually a pretty problem in and of itself, and then come back to Floquet. Okay, now I'm probably going, I have no idea where we are on time. So what is my target time to finish?
About 12.
Okay.
Sorry, no, about 12.
So, okay.
Including all discussions.
All right. Best thing would be following Pierce's, please complain as we go along, so that way I'll get to the end and you would have asked the question. I meant to say Pierce's, and you were saying which is the usual division of labor.
They didn't even know it. So fast.
Very good. All right. Okay, so here is the transverse field Ising model. As you know, one of the great contributions of quantum information to our field of condensed matter physics was to persuade us all that we should stop writing sigma z and just write z. This really is helpful beyond the point. So this is the exchange term in a Ising model, and that's the transverse field. And I've written down couplings that will vary from site to site. So I have in mind a one-dimensional chain. So these numbers will be random. Without loss of generality, I can pick all of these numbers to be positive if they were of opposite sign. I can just go through and, in a one-dimensional chain, I can just flip z's as needed and flip y's as needed and get back the same Hamiltonian with all positive j's. So, of course, if these couplings are uniform, right, that's the sainted Onsager Ising model done as a Hamiltonian, and that has this well-known sort of phase diagram where at zero temperature, you have the ratio of transverse field to the exchange. When that ratio is very large, you try and make this term happy, and your system is a paramagnet. All spins point along the x direction. But in the z basis, that just looks like a complete superposition over all possible configurations. Whereas if this term dominates, well, then you want to make all the spins either parallel or anti-parallel, and that's the paramagnet. Okay? And then you have these sort of dashed lines, which are crossovers. But really what's true is that at any non-zero temperature, the system is in a paramagnet, right? Because it's one dimension. And at any finite temperature, you get a finite density of domain walls, because they only cost over one energy in system size. And so as long as those domain walls are dynamically free to move and delocalized, basically this is called paramagnet. Then you talk about crossovers and quantum critical regime and so on. But basically paramagnet, 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 right? That's the story. Now, if you make these couplings random, so this is again a famous problem that was studied for many, many years. And so what was done was what you would call equilibrium calculations, assuming that you could work with the Gibbs state. And what that did was it produced a beautiful story of the transition between the paramagnet and the paramagnet, which is the so-called strong disordered fixed point, which I will not describe. And then, a modification of these crossovers, interesting scaling, then with randomness, so there's a question of different configurations. So there's an absolutely beautiful story. I guess maybe Daniel Fisher was the person who contributed most to it, although there's a prehistory and a post history. But again, for our purposes, the only thing we care about today is that there's a paramagnet at 0 temperature at any finite temperature in that story, everything is a paramagnet, and likewise this axis is a paramagnet. Because at the end of the day, this is a symmetry question. It's the discrete symmetry you're trying to break in one dimension, and at any finite temperature, you cannot break a discrete symmetry in one dimension. So if you think you're doing equilibrium physics, then you can prove that you cannot have this sort of long-range order. And the way that works is more or less you assume that you have a density matrix and you break the symmetry, and you can come up with a contradiction, and from it you can construct another density matrix which is better for equilibrium purposes, which is favored by Simon and Tokal along those lines. Now, what I want to tell you is that what we realized in this work that I referred to, that this is just flat wrong. Okay. And the reason it's wrong is not that the calculations were wrong. It's that in this particular system, non-zero temperature has none. And the correct phase diagram is not that you put a temperature axis, but that you put an energy density axis. And when you put an energy density axis, then you find a phase diagram which looks like so. To the left of a certain critical coupling, the ground state is paramagnetic because I picked all the J's to have the same sign. And then you have a set of many body eigenstates going all the way up. And each one of them breaks the Ising symmetry of the top. In the ground state, everybody agrees. In these excited states, you have some number of domain walls, but the domain walls are stuck. They are localized. But as long as they're stuck, as you walk through the system, there's an up domain, there's a down domain, up domain, but the Ising symmetry is clearly broken because the local expectation value of the spin, the z component is non-zero, and that's what you would call a spin glass, in the sense that it's spins are in a random configuration, but they are nevertheless frozen. Right? Phase introduced by Peterson's thesis advisor.
But you're looking at a finite transverse field. So how do you take some confidence to know that I should think in sigma z?
No, so right now I will offer you a cartoon. That cartoon applies along this line. And then you have to
Okay.
and then you have to show that that cartoon is stable to the inclusion of the transverse field. And that's where the many technology then got localization comes. Yeah. And so it will still be true because of symmetry, but the question will be asked. The answer is what's the expectation value of the local z, and that will go as you march along this line. It will go from 1 or -1 to basically having a value of 0, which will then persist. So okay, so notice how weird this is compared to what I wrote showed earlier, which is if normally you would think of this as temperature, and this is sort of like saying in one dimension you can break a symmetry at any temperature. That of course can't be true, and it isn't, but it is true at any energy density. Right? So okay, so that's the claim that's the correct phase diagram. Now I just offered the intuition and answer to the question that well, maybe let me see what I have on the next slide. Okay, let me do this slowly. So when I have only the transverse field, then its eigenstates are trivial. They just look like you go in the X spaces and put down a list of numbers, and you can read out the energy by just putting those numbers in here. Right, so I've got a list of eigenstates which are spread over some energy range, which scales with the number of spins and obviously involves the average values of the transverse field. There are 2 to the n such states. Right, so like all many body systems, the spacing between neighboring levels is exponentially smaller than n, taking basically n dividing by 2 to n. The states are extremely close. Now, something which is kind of obvious from thinking about this is that the neighboring eigenstates in the spectrum actually are wildly different. And the reason is that if you think of this function, right, imagine picking a particular spin and flipping it in the X spaces. By how much did the energy change? When it's twice the local value of the field, right? That number is order 1 in system size. Whereas you know from counting that the next state over must be ordered e to the -n or 2 to the -n system size. Right? So flipping one spin takes you quite far up. You've got a fraction of the spin to undo it, and then maybe a third and maybe a fourth, and actually you roughly speaking have to fiddle with half the spins before you found the next energy level forward. Okay. Now, are you with me? So if these numbers are random numbers, random positive numbers, doesn't matter, random numbers, finding the next configuration over requires you to do a macroscopic rearrangement of the values of the spin. This is a big deal because ETH is the opposite point. ETH says you can't tell the difference between this many-body eigenstate and the next one over for the purposes of calculating expectation values of local free-body operators. You have to be that one. So this is trivial, but it tells you that we have violated ETH. Now, of course, it's also trivially true that such a Hamiltonian does not obey, it's not going to exhibit stat mech behavior because each spin is its own little universe, right? And so there's really no way for it to equilibrate. The spins don't talk to each other. Whatever state you freeze in at the start, so to stays.
So I think you have your z-axis couplings.
Well, right now, I'm just going to be extreme.
Just doing this.
Yeah. And I'll just say that in a second.
But what about if you consider spatial correlations between disorder?
Spatial
I
correlation.
mean, you assume in this, well, if the disorder fields are correlated between different lattice sites.
I mean, obviously, if you make them all uniform, I mean, that sounds, I haven't thought. Maybe if you make them very, very long range, but in any short range case, this would be fine. Okay.
It's just like
Yeah,
a
yeah.
trivial question. So you said that we're not looking at temperature, we're looking at energy density, and these two are not the same because it doesn't thermalize.
Yes.
But then what exactly do you mean by energy density without something else if there's not a thermal ensemble?
It's the expectation of the H divided by N.
In which state?
Oh, in each of the eigen.
In every
in every eigenstate, yeah. So that was the plot of eigenstates.
energy density.
Right, each, because yeah. So in this picture, currently I'm doing this as energy.
Okay.
Right, if I divide by N, there's my energy density.
Yeah.
Right, and that will be over a range of over 1.
Okay.
And then as I take the limit N goes to infinity, they will become extremely dense. And then I'll talk about, and in that limit, I'll talk about an energy density. I'll have a continuous range of energy density from the bottom to the top, and that will help you. But I mean, the system, I got I'm talking about many body eigenstates and their energy density. Energy, if you will, just density, just to be able to take.
Okay.
Take them. Okay. All right, good. So Piers asked, what about the exchange, which is obviously the key question, which is to say, what an exchange does is, the two spins, let's say, in the x direction, well, it can flip them, the ZZ term, even if it's 2, maybe, So any localized disturbance, obviously, in principle, can propagate under the action of the exchange term, right? So if we're doing it, and the whole business of trying to convince yourself that many-body localization holds is to convince yourself that if these numbers are sufficiently random and the J's are sufficiently weak, that this does not happen. It does not happen with high probability, but does happen in sources that, it's not like single spins continue to be a universe unto themselves. You get 2-site resonances, 3-site resonances, k-site resonances, but with a probability which gets smaller and smaller and smaller. So it's an extreme version of what happens in Anderson localization, where you start on a site and you ask what happens, how many sites does the wave function spread over. Okay. So again, this is a very subtle topic, which so far every passing year people discover new things, new resonances which they had overlooked, and so first it was the discovery that MBL above dimension 1 was unstable. More recently, it's the discovery that even the phase in 1 dimension is smaller than we thought. let's say it's a subgroup. But we will assume that there is a relief, which is the carbon gas consensus in one dimension, where so at sufficiently small J, we will use standard law to argue that this localization is stable. What that means is that these things that I began with, these xi, which obviously commuted with the Hamiltonian, will evolve into objects often known as L bits or local integrals of motion, which are sort of spread out versions of the local x's. So it's sort of the local x plus stuff, which sort of goes away, and that I have n such objects will commute with the exact Hamiltonian, which is now not just this, but also that plus the extension. So far, so good? Yeah. Things here? Okay. All right. So that's the story in the paramagnet. And then on the other side, I have this Hamiltonian, and that one has eigenstates which are in the z basis. Those also are spread over a range, which is basically the average value of j times n. With one thing that each one of them is twofold degenerate, because of course, since it's an Ising symmetric energy, if you give me a particular string of z's, you can just flip them, right? And I'll call minus z's z bars if you don't mind. And so if you have a z, you must also have a z bar. So that's why I put the factor of 2. But apart from that, it looks a lot like what we just said for the paramagnet. Again, in this extreme limit, you know, the eigenstates are trivial. They just look like classical Ising configurations, which have some domain walls. The domain walls sit exactly where they are. The system is localized, nothing is moving. ETH is violated because as you go between one configuration energy and the next one, the location of the walls changes completely. All right. And then you argue that this is stable to the inclusion of weak transverse fields. And they do one thing though, which is they select, as usual, for cat states, which is to say, if you have this up and down pair, right, this Ising reverse pair, at any finite system size will couple because you go through the transverse field and put this one and that one and that one and that one, right? So you basically get gamma to the length of the system, which is exponentially smaller than the length of the system. So you get this tiny splitting, and apart from that, you'll more or less get what you have. So far, so good? Yeah.
So I'm sorry, why do we get a different configuration of domain walls every time?
Well, I mean, the thing is, the ground state is all up. So the next one over in the wall, one domain wall, two domain walls, and three domain. But the thing is, these J's are random, right? So the same thing, the argument I gave before. If you, let's say you introduce one domain wall, it's an energy cost of size 2j, 2j average roughly. But in fact, the next one over is exponentially close. And that is again the conclusion. Well, you do that and move this around.
Okay, I see.
Yeah, it's the same argument. Pretty much.
So when you say stable, I mean the ETH breakdown is stable.
It is, that's localization stable, and so therefore you will have a modified set of z operators which will be the Hamiltonian. They will depend on exactly the values of the couplings and exactly the values of the transverse field. But and so the story will be stable in the sense that the exact eigenstates will continue to break the Ising symmetry. They will have this sort of form. System will be localized. And okay. So the symmetry statement I just made. So in the paramagnet, if you think of these x states, right, and you just look at the expectation value of zi, zj in a given eigenstate, and you look at them at long distances, well, in that case, it's trivial. You've got this string of x values, right? And you act with z flips x, so obviously you're not going to get the same state back on the left, so it's trivially 0. In the spin glass, it's equally trivially non-zero, right? And just to be careful, I want to do it in the cat states. So I have in each eigenstate on one side, I break the Ising symmetry. In each eigenstate on the other side, I don't break the Ising symmetry, and then I've argued that this symmetry breaking and non-breaking continues into the phase R. Right? Okay. Now, the particular problem we've been looking at, the transverse field Ising model, is very special. Right? As you know, it's solvable by free fermions. It can be reduced to a free fermion problem. And of course, when you have free fermions, right, then you solve for some single particle states, and then all many body states are simply constructed by occupying. Right? So that's so what happens in that case is that if all the single particle states are localized, then it's trivially true that at any energy density, you're going to get in any one of those clusters. That's why the phase diagram I drew as a function of energy density is exceptionally simple. And that's because there's an underlying free terminal. Make sense? Please ask. Yeah.
So that means that if any model is like, well, you can write it in terms of free fermions, it will also have like such simple diagram, provided you have localization.
Yeah.
Okay.
I mean, let's say, you know, 1 or 2 dimensions in the standard Anderson class, which this isn't, got my runs, but you know, once you, if all the single particle orbitals are localized, you can make any body state you want.
So then, for instance, we can take like honeycomb model and see the same diagram if you introduce like quantum couplings.
Presumably, you mean when I go to fermions, yeah. The only thing is with you know, there's the standard Anderson class, which is direct fermions, but the this one, for example, is Majorana, so which is why there's a critical point. It's not the thing that so the honeycomb. I just don't remember off the bat what happens with 2 dimensions for that universality. Okay. But the basic idea is correct. Okay. All right, good. Now, I could add other terms to the Ising model, which in the language of fermions induce interactions. So now this is a more generic model. And so that's actually been studied. This is not the most recent rendering of the phase diagram, which is in this paper. Which again, I apologize, I didn't look up for you, but you probably don't want every single detail. And so basically, if you make the interaction strength strong enough, you can actually destroy both the paramagnet and the spin glass and end up with a thermal phase, which is our old friend with the infinite temperature state. And along the way, you can end up with a situation where the paramagnet is stable and the spin glass is stable, but in between you get a inclusion of a thermal phase instead of just having a single value of the constant. So that's the more generic. So yes.
For the fermions, how do you characterize the spin glass phase? Is it just regular inducing?
So this is actually, funnily enough, it's these edge modes are the easiest way to say. Of course, you can calculate the spin-spin correlation function of the language of fermions, which involves our strings.
Yeah.
But the easiest way to see it is that these derived edge modes are present in every single eigenstate at any. So so that's the natural fermion analog of what's good.
Thank you.
Yeah. Excellent question. Thank you. All right, good. So far, so good. All right. So we made the argument that when you study the eigenstates, they do very different things on one side or the other. And of course, the system is localized. So instead of, we should go back to the question of, you know, in an experiment, in my sense, which is in some device, which what would we see at late times? Okay. So, and how could we detect this distinction between the two phases by looking at it? So what we do is we can feed it a starting state which breaks the Ising symmetry. So maybe this is 1 and the next one is -1 and some particular sort of sentences. Okay. In the paramagnetic region of the phase diagram, when you look at the late time state, you will find that the late time state no longer breaks the Ising symmetry. If you examine the local expectation value of a given spin z component, it will go to 0 at all times. And in the spin glass phase, on the other hand, it will. Right? So you bias the system by giving it an Ising symmetry weighting state, and you ask it very late time, does it remember this or not? And in the spin glass, it will, and in fact.
I follow up with my last question. I'm sorry, I don't understand how having play of edge modes is the same thing like
It's not obvious.
Is there a simple way of getting the connection? Because I appreciate it means something exotic is happening. But
No,
it's not
there
the
isn't
same thing
actually.
as saying that you have
Yeah.
an exponential number of states.
No, it is, and the reason it isn't obvious is it's not even necessarily true, though, is that in the clean system, it turns out you can find these things which Chris Lauman discovered it when we were thinking about it, but later Paul Friendly and particularly what they come to be known as strong edge modes. And
Why don't they just in regular engines?
well, the strong edge modes in the sense that they're there when you think they shouldn't be there, and then you're at a clean system at a finite energy density, and you end up with those. So there's not a simple and obvious connection. So one, you can just calculate the string order from the matrix. That's just the straightforward thing. It is also true that if you study the disordered Cation chain, that you do have localized edge modes. But I don't want to oversell it because edge modes can be very distinct for reasons which I'm not so not concerned.
Thank you. So it's not up. I just wanted to check.
No. We thought it wasn't, but we quickly discovered by looking at the clean system, that it wasn't. So
then how do you know it's a spindle? When I asked you before, I thought it was a spindle.
no, I can look at the string order. Yeah, I just calculate. I mean, the thing is the fermions I can construct spin wave function starting from the fermions.
At the calculation, you have to include time.
No, because everything I was describing was in each eigenstate
Oh, I see.
I can examine.
Okay, thank you.
Okay, so I think I said this. Okay, so I just want to just digress a little bit for pedagogical purposes. So, the way we think about this whole class of things is you've got some Hamiltonian, it's got exact eigenstates and energies, and the initial state is some superposition. And so the expectation value of some operator, you just stick it in and you get two classes of terms. When the energies are the same, they drop out, and when the energies are not the same, you get terms that oscillate. Right? So what we say is, well, as the time becomes very large, this set of terms sort of cancels out because there's this stuff that's sort of oscillating. And so at late times, you reduce to the first term, which can be, there's still life there, but basically that's sometimes called the diagonal ensemble. Maybe a better name is the block diagonal ensemble. Okay. All right. So in the paramagnet that we did experiment, what happens is each state is more or less unique. It's not more or less unique, it is unique. There's no multiplet structure. Right. So in the paramagnet, each state is on its own. In the ferromagnet, remember, there was this two-fold identity. Right. So in the paramagnet, if you go back to this expression and you say, all right, if E nu is equal to E mu, there's only one state. So it's basically just a sum over mu. I've got mod C squared and then the expectation value at that state. Right? So far, so good? So that leads to this expression, often called the diagonal ensemble. So you would say that at late times, the expectation value of some operator is reproduced by this ensemble, in which half the information that was present in the initial state has been lost, the phases of the coefficients. But the other half of the information, which is the amplitude of the coefficients, are still present. And that's going to be what I see. If, by the way, ETH further held, then this expectation value would be independent of the state. I could pull it out, do the sum, and end up with something which would then just be the expectation value in any state in the value density. So the ETH argument proceeds by saying, I've got this time-dependent form, I collapse with a diagonal ensemble, further the ETH holds, I get back a unique answer independent of the states that I can get. But if the system is localized, I will end up with an answer that does depend upon the initial state, but not totally. Half the information is erased, the other half of the information is still there.
So if ETH breaks down, can I then say that the system is localized? Is that too strong?
Comes back to your earlier question, which is to say, I mean, people have discussed partial breakdown of ETH and so on and so forth.
Oh, because it depends which.
Yeah. I mean, presumably that if we find intermediate, well-defined notions of partial orthodoxy, really some connection like that. Okay, in the spin glass, I need to keep the fact that for each there are these doublets, right? So ignoring the exponentially small splitting between them, the doublets are degenerate, right? And so now I've got to keep those. And so what I've written here is to say there's a mu and then there's a sigma, which is the plus or minus. So there are two caps, right? The plus cap and the minus cap. And so I end up with something which is more complicated, which is why I said it was not that. Without going through the details, it's really, it will just take you 2 minutes with a piece of paper. You can convince yourself that these lifetime forms recover the claims that I made earlier, namely that in the spin glass phase, you can expect to see eigensymmetry breaking, and in the parametric case, not. And so the late time states are actually informative regarding the symmetry breaking. So I want to emphasize that while I don't have thermalization, which is the independence of the late time state on the choice state, there is dependence, but there's enough universality that I can tell whether I'm on one side or the other. And given it, I should say, I'm going to know. Yes, sir.
You have a separation scale gaps between like cap and.
Yes. Yeah.
So we're putting the plane.
If it was a finite volume, then once you get long enough time, the exponential is long, you would resolve the thing and then you would go back to not the. So in other words, ultimately, if it's unique, then
You gaps are extremely small. These gaps are also.
yeah, but most of the gaps I don't. Well, yeah, but it's not. So the thing is, a lot of the things that we are washing away, most of these differences are not exponentially small. Because everywhere in the spectrum. So lots of stuff goes away much faster. It's only the stuff that's very, very close in the Berkeley composition. So I hear what you're saying, which is so actually in the phase diagram, so if we really want to carefully discuss this sequence of scales and finite volumes, we can. We will find, for instance, that there is another line in the phase diagram. In one side of it, the cat splitting is the smallest one. The other side of it, the cat splitting is larger one. And so forth. And that sort of commencing yourself. So the finite size effects are recommended, but apart from that, the picture I described is morally correct. Obviously, I should be somewhat careful. For example, and it's also that this is something else, which is to say that the cats have a very special relationship, which makes certain matrix elements very large, which is not necessarily going to be true of two generic nearby states. And so when we study something like Z, it's something that is designed to be a large matrix element between the cats, but not necessarily going to be a large matrix element, a single Z between two neighboring ones because they differ in lots of places. So there's also a story in the matrix elements which are not used correctly. All right, excellent. Okay, so putting all of this together, right? The statement is that look, here's an MDL system which can exhibit eigenstate order, eigenstate phase transitions, and that terminology has come to mean that eigenstates and eigenvalues can show singular changes as parameters vary, even when ensemble averages are small. So now, ex post facto, this is actually a rather natural possibility, right? That if you wanted to know if there's a phase transition, you have a Hamiltonian, the matrix. Of course, you should look at all the eigenstates and eigenvalues. Why wouldn't you, right? But we don't, at least historically, we stopped looking because what happened was we can look at the ground state, but after that, it was the right kind, and you knew that if you said use statistical mechanics, calculation simplified, maybe there were field theory techniques, you could do path integrals, all sorts of wonderful stuff could be done. So there's the idea of looking at many body eigenstate could have struck everybody as being slightly insane. It's a waste your time. Okay? And so it's actually very natural, but it was not something that needed to be done until this MDL problem came along. It turned out to just look. By the way, another example of a eigenstate phase transition is what is often studied, is a one-dimensional Hamiltonian with no other particular structure, but which has an MBL phase and an ETH phase, an ergodic phase. And here, for instance, what happens is we look at the eigenstate, and you're going to see a difference between the volume law entanglement and the area law entanglement. The level statistic we can put the Poisson on one side to the Gaussian. But again, if you just look at a common average, you see it's the probably then the phase transition.
I'm sorry, by understandable averages, you mean like like taking a thermal density matrix, or you mean?
Yeah.
Okay, so not average over the solar or something.
No, if I calculate with the density matrix,
Yeah.
with the Gibbs state, yeah, which is what you would have done otherwise. Yeah. All right. So let's see, how are we on time? 24 minutes to go. Back to Floquet. So I need an Ising model for Floquet, and what we'll do is we'll break up our Ising model into two pieces: the transverse field and the exchange, and construct something which we call a binary drive, namely, for part of the cycle, we act with one, for the other part of the cycle, we act with the other. So that's the simplest Floquet model that you can put down, and that turns out to be enough to discover something quite pretty. Now, I'm going to draw a phase diagram in a particular lift, just because the phase diagram is a nice and simple limit. I'm going to assume that these numbers, they are random, but their variance is very, very small. Specifically, I'll take the infinite volume limit first and take the variance to 0 later, because as I take the variance to 0, there will be some localization length which will get to be very, very big. But if my system is infinite to begin with, right, I can live with a very, very long localization length. So it's just an order of limits to simplify life. And when I do that, and I solve this problem, I find the following phase diagram, including the colors. They all come there. Okay, so something which I sort of had there, maybe, really it's the product of this and the time, right, which is the dimensionless number. Here I've chosen the couplings to have an average value 1, and so then it's the times that I end up plotting, but I could have done it the other way. All right, so I'm going to explain where this phase diagram comes from by basically walking you along the boundaries of the phase diagram. By the way, it's not like it just suddenly ends here. You could go for longer times. For instance, this phase will turn out to be, part of a kite, and so on. But this is sort of the central region which will. Okay, so what's going on here? This will be the paramagnet. This will be our old friend, the spin glass, and these will be two new phases: the 0 pi paramagnet, and the phase initially called the pi spin glass, and now famous as the discrete time crystal. All right, so how can we rationalize this phase diagram? Okay, so along one, which was the horizontal axis, the unitary is very simple. I only act with the transverse field, right? So of course, basically just the Hamiltonian problem. If I really walk along that line, the eigenstates are just assign every spin a value in the x basis, and the eigenvalues now, instead of writing eigenvalues of h naught, I put them in exponentials and they become the values of the unit. So far so good. Okay. And since it's a unitary, its eigenvalues live in a circle, and I can mark them in the circle, and they will sort of be, spread out roughly uniformly, but with nearest neighbor, with near direction, level response. Along 2, which was the axis along this side, I have the opposite thing. I don't have the transverse field, but I have the exchange. Okay? And then again, if all I'm doing is having a time independent Hamiltonian, it's my old friend, it's the spin glass with these cat eigenstates. I don't have to take them to be cats, I have to take them to be separate, and the eigenvalues look like that. So each one of those is twofold degenerate, and here is the paramagnet. Now, the part that's not so trivial is to say that if I move inwards, now what happens is I'm mostly doing the paramagnetic drive, but I'm also doing a little bit of the paramagnetic exchange drive, right? So now it's a genuine Floquet problem. Things aren't varying with time, and I do need the localization in order to do this properly. And the claim is that in the limit that I described to you, this region will all end up being effectively paramagnetic. Again, for the pre-Fermion problem, we can do it explicitly, more generally, this region will become, more complicated. All right. Likewise here, you can move in and you will find that the spin glass phase will persist. So these are, we call them the type 1 Floquet phases, the idea being that these are Floquet phases, which are Floquet phases. It's not a time-independent Hamiltonian, but they are modest variations of what you would get if you didn't have time. These two, however, are type 2 Floquet phases, which are very new. All right, so let's march along line 3 and see what we find. So notice the number pi over 2. So with pi over 2, you're going to stick this up here, right, in the transverse field, and this is the exchange part. Now notice that this just factors. So each individual spin, I'm acting with e to the minus pi over 2 times x. So since the spin operator is 1/2 of Pauli, I'm basically just doing a rotation by pi about the x-axis. So if the spin with z, up, right, pi rotation means this one goes minus. So in fact, each individual operator is just the x for that particular spin. It just flips in the z basis. You can explicitly exponentiate. There are a few factors I in general. So this unitary is the global spin flip operator times the zero spin glass unitary, which is just the exponential of the standard extension. It's a very simple but nice unitary. Now, the fact that I have this p in here, in fact, means that the eigenstates have to be Schrodinger cats. Okay? And that's because if I tried to feed it just z, the p would flip it to z bar. This thing would measure its energy, right? If I fed it a z bar, the p would flip it to z, and this thing would measure its energy. The energy would come out to be the same because it's eigensymmetric, but obviously I can't just do z or z bar, I have to be able to go between them. And in fact, if I just make plus minus linear combinations, the cats, I get plus minus 1 times that Eigenstate. So it's very simple arithmetic, but that's the heart of the matter. Okay. So when I examine these eigenstates and eigenvalues, I say on the circle, I've got doublets where one of them sits here and the other sits there. So in the zero spin glass, I had doublets where they both sat at the same place. In the pi spin glass, I had pi doublets, they sit diagonally across from each other. But there is this feature of the spectrum that I've got these doublets. Okay. All right. Finally, I can march along the line which was the top part of the phase diagram. And so there, it's j that's pi over 2, and the x field is whatever it wants to be. So again, each individual term is basically just a Pauli. Product of two z's is also a Pauli, squares to 1. So if you expand this out, much as I got a product of x's, I now get a product of z1 times z2, z2 times z3, z3 times z4, right? So all the z's cancel except the two ones at the end. And if I actually have a periodic system, all of them cancel. So with periodic boundary conditions, actually, this goes away altogether. And my unitary is exactly the same unitary that I had for the trivial parameter. But if I have open boundary conditions, I end up with the z at the left and the z at the right. And now if you ask what are the eigenstates of this problem, well, you'll discover that they come in quartets. Two of them have exactly the same location on the circle, and two of them sit diagonally across. So this kind of phenomenon where periodic boundary conditions don't give you anything interesting, but open boundary conditions do, is of course what we've all come to know and love as symmetry, SPT behavior, of which topological insulators are an example. And so what we've discovered here is a Floquet SPT, in which a system which is basically a paramagnetic but has boundaries. Using freedom, which are non-trivial and tell you that you're there. All right. So just to go through the cookbook, what I've shown you so far is that if I had this phase diagram, I look in 4 distant regions, and I discover in each case, in 2 of them, the eigenstates of the unitary break Ising symmetry. That is on the left side, the 0 spin glass, on the right side, the pi spin glass. In 2 of them, the bottom and the top, were paramagnetic phases which do not break the Ising symmetry. And the spectrum has different structure. In this spin glass, there's a doublet structure. In the paramagnet, it's unique. In the pi spin glass, there's a pi doublet structure. And in the 0 pi paramagnet, we open boundary conditions, there's a quartet structure. Right? So you see the basis for having 4 different Floquet phases because the eigen spectrum, right? The eigen system is singularly different. You can't get from one to the other without something interesting happening. Okay, so the last bit was how do we see it? You can see it with the technique we already developed. We'll feed it something, go to late times, let's see what happens. We'll feed it with an Ising broken symmetry phase, for example, state in the paramagnet, all these expectation values will vanish. In the spin glass, they will be non-zero, as we discussed earlier. And in the pi spin glass, what will happen is that the expectation value of z will actually oscillate. It will be sort of, plus minus 1. I haven't quite discussed it. We can come back to it, but it's true. And in the 0 pi paramagnet, in the bulk, it behaves like a paramagnet. The boundary spin will actually show you this oscillation. So this doubled period will appear in the bulk in the pi spin glass and at the boundaries in the 0 pi paramagnet. So that also tells us that in an experimental setting, we can feed it a state, look at late times. And
Are you going to say something about something off these axes, the outer axis?
so the same thing, which is you can, so the free fermion problem, you can numerically solve it and check that it's true. In terms, when you start to make it interacting, then in fact the middle region becomes a problem. Much as the earlier, so in fact it's a more complicated phase diagram. But in the free fermion case, and the shape of the phase diagram was specific to the order of limits I took because that's very close to being clean. The shape also distorts, but if all you're doing is free fermions,
So it was a specific limit that the variance goes to 0.
yeah, so
in
that
some
gave
way,
us
which
these
is-
nice lines.
Yeah,
But
exactly.
the topology of the phase diagram
Would be the same.
actually that I'm not sure.
Yeah.
Remember that. It could, yeah. Those 4 phases are the only things you get for the free fermion problem.
Right.
You basically localize acceptable phases. It could be that the topology, maybe 2 of those, I don't remember now, whether if the topology can change it, but the fact that there will be lines of phase transitions and basically phases is true of the free fermion problem for the same reason that it's just an underlying single particle problem. And the interacting one it becomes more complicated.
And in the interacting one, is any of those phases actually surviving?
All the phases survive. It's just that in addition, in the middle, you get an ergodic phase.
Right, okay.
So you can add weak interactions. So there is such a thing as Floquet in the L.
And for non-zero variance, does it make a difference whether you have a bounded distribution or tails?
Look, all of these questions basically turn on, whether what your beliefs are regarding MBL. So whether it's Shivaji or not. There's no detailed study of that kind. The Floquet case is somewhat more delicate than the Hamiltonian case, and I don't know. The detail. Okay, so this is actually my last slide, and this was just to say, so the Ising model already tells you the sort of stuff that can happen. There's a zoo of SPTs that were found. One case by, well, I really should have said at the start. So this is work that with Robert Mosner, with Kakimani, Achilles Lazaridis, and then Kurt von Kajulek. And Kurt and I, mostly Kurt, classified SPTs as well as breaking states in this Floquet setting. The Harvard group found an interesting phase called the chiral phase, which in fact works very differently. I'm not completely sure I know the full list today. When's the last time I knew it was when we wrote this review. Benner, Rahul Roy, Franklin will be done. Things come back. And there are other reviews. So there are other Floquet phases which have been found. The one that has been looked at experimentally so far is basically the sweet time crystal of my spindles. In some ways, that's the. If there's one phase you should learn, it should be that one, like learning the Ising paradigm. It's the simplest thing that comes out of the simplest model. Already tells you something quite big. That's the end of my first talk. So.
So we have about 10 minutes for further discussion, bearing in mind that we also have another talk this afternoon.
And bearing in mind that we're also happy to relax.
Yes.
Yes, please.
Embarrassingly simple, but can you define what ETH really is?
Well, so it's there are two parts to the twine. That if you have a system that obeys sort of mechanics, that for some class of operators, which I think the current claim is, if you have just sort of n spins and you study k body operators, I don't think they have to be local. And I think if k is can more or less butt up against half the system size, as I recall, for this large family of operators, if you then calculate their expectation values in each of the many-body eigenstate, and what you'll find is it's a smoothly varying function of the energy density, so that nearby eigenstate, actually nearby meaning really nearby in energy density, given energy density, which is a lot of states because they're exponential, so they will give you the same answer. So you can plot that versus energy density and find basically a smooth curve in the limit of large systems. So that's one part of it. That's diagonal pH. Then there is a statement about the off-diagonal matrix elements, which is comes from sort of random matrix stuff, which is that basically a given state couples to a lot of states with sort of random signs and so on. I'm not sure I could immediately write it down without doing something wrong. But those are the two parts. So the second part is important when you start thinking about response. And the first part is important when you talk about reproducing via the late time state, the expectation values you get to pure just doing statistical dependence.
So once I have that smoothness, I can sensibly define maybe an entropy or something on this energy.
Well, it's really about expectation values, not so much about entropy. It's about the thing is, equilibration is you start something and then you let it run, right? In statistical mechanics is I average over states in some way. So the question is, why do these things match? Right. So Zelinsky's answer was, well, supposing at the level of individual n-body eigenstates, you sort of have a. Okay, but by the way, here's another nice word in ETH, which is I'm not saying they're all reversing mathematically equivalent. Supposing you take a single eigenstate in a very large system, and you pick a macroscopic subsystem. So you have a subsystem, itself macroscopic of the system to be big. And then you calculate on the subsystem the reduced density matrix by tracing over the outside. Then, up to boundary term, the reduced density matrix on the interior will look like the Gibbs stuff, with the Hamiltonian restricted to that. So that's
And one can show that these two statements are identical, because I thought the second one was what one should consider eigenstate formulation. Even for reasonable cases.
So I'm actually off the top of my head, I don't know the answer. Maybe Ising does. I think these papers by Deutsch may have something to that effect, but it's a good question. I've never put them together myself.
Thank you.
Sure.
Follow up on this.
Yeah.
This was about eigenstate normalization, and now about the hypotenuse? How far is the hypothesis?
Well, okay, so there's not to my knowledge, anything approaching a Elliott-Lee-Leonard proof that if you handed some integrability broken Ising model, that you could start from that and show it. So there's numerical evidence, obviously, that way. So in that sense, it remains a hypothesis.
With counterexample?
Oh, and yeah,
Yeah.
yeah. So there's certainly Hamiltonians that don't do that. On the other hand, there are Hamiltonians that do seem to do. So it's both, it's a natural resolution to the question of, look, I mean, when I was in graduate school, the textbook, mentioned it, standard that textbook, and somehow there was all the classical part, which at least it was clear what the claim was, that measuring the time average and system flow the phase based on so. He came to the quantum state and everything was well within an eigenstate nowhere. And so ETH is a natural answer to the eigenstate itself is good enough. So it's a very natural answer, but I think an actual proof. I think a simpler thing maybe is just to show that random liquids that if it's whole, pedigree. What's the name of the conjecture?
It's long link.
Yeah, the photographs or something like that, which is to say that if I hand you a generic many-body Hamiltonian, that the nearby negative statistics is in fact in Gaussian. I'm not completely sure what the status of that is either. Of late, people on the string theory side, like Sue Schenker and Doug Stanford, and there's some time to think about that. But I don't think we're. I don't think there is a willingness to make that connection tight, which would be a sort of illusion. Some problems you can always joke and say one man's bigger than another man's lotus, but in this one, I'm not so sure. Yeah.
What is the connection between many body localization as hypothesized in the context of electronic systems in higher dimensions and many body localization you talked about, which is to be connected with temperature and low dimensions?
So the thing that David Hughes and William Oganessian contributed at some stage was to point out that the original arguments, which were known for electronic systems by DOA, that when you applied them to spin systems, they also apply to infinite temperature. And that just simplifies a lot of work when you do it. But of course, they began by just porting over the argument that, about fermion and then make it a reference system that would expect that we will come any more directly there. So that's I think one thing. The second thing is the original work suggested that there should be this many-body mobility edge, which is to say, localized below. That's turned out to be, I think as of today, I think most people's belief is that if you've got on a lattice system, either everybody's localized or they're not. That there isn't such a thing as many-body mobility edge. I don't know what the beliefs of VA themselves are. I haven't run into it. Because that sort of suggests that, yeah, so am I correctly summarizing the beliefs of so that's almost as if the VA problem itself, I suspect people will say, doesn't really have localization, but maybe it really mistakes in boundary over space to get it. But look, some of this also ends up being, things can be very, very slow and be localized for a very, very long time. And so a lot of this we're now trying to decide whether it's really, truly infinite time.
Is infinite temp just a simplifying feature, or is it actually essential element?
No, it's a simplifying feature because you can come down in energy density and things are very easy. It's just that you can show it in.
And what about one dimension versus higher dimensions?
Yeah, so the current belief is that once you leave one dimension, at least if you have random disorder, that you have processes that ultimately destroy complexity. And that's this business of rare regions and droplets and so on, which is, your former colleague Marcus Miller, began when people have worked on it. Now, there are quasi-periodic models of localization, and there I think the belief is still they don't have the rare regions. So presumably, those can continue to exhibit localization, even in high dimension. So, but basically, you get some rare region which is not particularly localized, and then the challenge becomes that is able to then start delocalizing stuff around it. And so then there's this avalanche, this stuff happening, sort of propagates. It's turned out to be a remarkably subtle problem. And I would say that the main thing, in some ways, post-BAA is kind of the revenge of finite dimensions, which is, BAA was done on this thinking, thinking of a box-based graph. And that seemed not to care what dimension you were in. It was just, it was in a very different sort of way of thinking. But all these rare region effects very much, Griffiths type thing, the thing that actually care about the fact that it was 1D versus 2D versus 2D. The spatial localities have had its revenge since the end of the world, which is kind of nice as physicists, but sort of annoying since we don't have the space exists.
And then the second aspect.
I think we better cut it
Okay,
off.
fine.
Because we really
Okay,
are running
right.
later, we'll have another talk this afternoon,
Yeah,
where I think we can have much more discussion. So my suggestion is we thank we take 15 minutes for coffee to hopefully allow us to have some lunch break later.
About 40 minutes.
Yes, we'll have 50 minutes for coffee because we need a break now. Back in 15 minutes and we'll work back. Sorry? Yeah.